In this lecture, we'll take a closer look at the concept of energy. I'll give just a couple of examples of the many different ways that energy can be observed, classified, or changed. Previously, we've learned that matter occupies space and has mass. Matter is composed of chemical elements which can exist as single atoms, or they can combine to form molecules and compounds. In this lecture, we're considering energy, and more specifically, we're interested in the ways energy can be transferred between objects or systems. From a chemical perspective, if we're thinking about studying chemistry, there are two different things we need to consider that we'll be looking carefully at in this course. The first one that comes up over and over again when one studies chemistry is the tendency of the universe towards the lowest energy state. The free energy of the system will always spontaneously move towards the lower energy state. The second thing we'll be considering in this class that comes up a lot because of the way that atoms are put together from charged particles is the fact that there are energy changes that can result from interactions between those charged particles. But before we get to that, let's just start by talking about energy generally and consider the tendency of the universe towards the lowest energy by doing some examples. The first example I want to show you deals with this tennis ball that's on the desk behind me. Which state do you think is the higher potential energy? Having the tennis ball down on the desk, or having the tennis ball up in the air in my hand? Okay, so a lot of you said that the higher energy state was having the tennis ball up in the air in my hand. And that's because I can let go of the tennis ball and it will spontaneously go down to the desk. Let's do that experiment. But what can't happen is the tennis ball can't spontaneously jump from the desk up into my hand, no matter how hard I try, because I'm not a magician. So spontaneously, the tennis ball moves from the higher energy state, which is being in my hand. If we were going to write that down, so the higher energy state was the tennis ball in the air in my hand. Okay? And the lower energy state was the tennis ball on the table. If we think about the process of me dropping the tennis ball, was the change in the energy of that process positive or negative? Well, the formula for the change in energy is given right here in this box. So the change in the energy of a system is implied there, although it's not written, is the energy of the final state of the system minus the energy of the initial state of the system. So the system here was the tennis ball, okay? And the final state when I dropped the tennis ball was the tennis ball on the table. That was a lower energy state. We agreed already. So that means that that number, if we're looking at the tennis ball, would be the smaller number. So we could say the change in the energy from dropping that tennis ball is the energy of the final state, which was the energy of the tennis ball on the table, which is a small number, minus a larger number, which was the initial energy of having the tennis ball in my hand. So the change in the energy for dropping the tennis ball is actually mathematically a negative number. Systems in nature spontaneously can give off energy. And the reason that that number ends up being negative is that from the system's perspective, it's lost energy in that process where it's giving off some energy. So I can draw a diagram over here. And you can do this for lots of different things, not just for energy. You can also do it for heat. I could say, here's my system. You can have all kinds of different systems. If something's coming out of the system, from the perspective of the system has lost something, and we say that it would be negative there. So if energy is given off by the system, then delta E, or the change in energy for the system, is negative. So this symbol, this triangle, is called delta. It's the Greek letter capital delta, and it means change in chemistry. If something is going into the system, could be energy going in, then from the perspective of the system, it's gained something. So we would say that's a positive number. And delta E, if the system is, for example, being heated or is having some work done on it, delta E then should be a positive number. And this works not just for energy, it also works for things like heat. So don't be afraid to think about what's happening from the system's perspective, because students a lot of times have trouble with the idea that the spontaneous direction of something occurring corresponds with the free energy being a negative value, okay? Because the system can spontaneously give up its energy, but it can't spontaneously gain energy. It would need the surroundings to do something for it to gain energy, and it can't do that by itself. But by itself, it can give energy off. Let's look at a couple of more examples. You can think of the higher energy state for some objects as sort of the cocked state. What am I talking about? Let me show you an example. Here's a little rubber band. It's a hair rubber band that I used to put my hair in a ponytail. Now, by itself, the little rubber band doesn't have much energy. I could drop it, okay? But if I dropped it, it would just go down. But I can cause the rubber band to have more energy by stretching it. If I stretch it and I point it at you, right? Now it's got more energy and I could shoot it at you, right? So by stretching the rubber band, by putting it into the cocked state, if you will, I have put energy into the system that is the rubber band. Now I had to do work to do that, okay? But if I let go, right, the initial state here is high energy because it's stretched, it's cocked. And if I let go, the final state would be it would fly through the air and it would land somewhere. The final state would be lower energy, right? And so if I letting go of the rubber band right here, the delta E for that process, the change in the energy of that process would be negative again. Let me show you one more example, and I wish I was Julia Child and I had some men down there to hand me my props, but I have to get it myself. So I'll disappear for a minute. Here I am. Okay, here I have a bow. This is a little toy bow that we bought as a prop for a costume party. And I have a real arrow on it, a target arrow. See the tip of it there? Kind of long. The arrow is for a larger compound bow, but I brought this little toy one because it's easy to see. Now with the arrow sitting on the string of the bow, you can see the bow if I turn it sideways there. Okay, there's not any energy in the arrow, right? It's not going anywhere. It's just sitting there. I can do some work to put energy into the system of this bow and arrow by stretching the string back, okay? So if I do that, I'm putting work into the system. Now, okay, now there's a higher energy state. So the cocked state here, which is the string pulled back and ready to fire the bow, that's the higher energy state. So if this was where I was starting, let's say this is my initial state, and then I shot the arrow, right? The final state would be the bow back to not being stretched, and I can't fire it because then I would shoot an arrow into my wall. I don't think that would be very amusing. Well, maybe it would amuse you, but it wouldn't amuse me. So if I let go, then the arrow would fly through the air, and the final state would be the bow no longer ready to fire, and that would be lower energy, right? So do you get the idea of what's higher energy and what's lower energy? This is the lower energy state, okay? If I stretch the bow back, that's the higher energy state, okay? So if this becomes my initial state, let's say this is where I'm starting off, right? You can say, well, the initial state's a large number, and the final state is a small number. What doesn't happen spontaneously is the opposite process. It's not spontaneous for the arrow to be pulled back, right? I had to put energy in to do that. So if I define this as the initial state, not pulled back, right? That's a small number, okay? And then the process of pulling it back is a higher energy for the final state. My arm is bent because this bow is too small for my draw length, but that's okay. So now I have the final state is a larger number. This is higher energy, right? So delta E for the process of me drawing the bow is a positive number. because that did not happen spontaneously. I had to do work for that to happen. So hopefully that's giving you some ideas about the concept of energy. We're going to do more examples along the way. Let me put my dough back down. Okay, so that's one part of our study of energy, and that is the tendency of the universe towards lowest energy. Okay? Systems in nature can give off energy spontaneously. They can have a negative delta E spontaneously, and that's the direction nature likes to go, towards negative Gibbs free energy. That's what we call downhill in energy, right? You can think of a ball on a hill. The ball spontaneously rolls down the hill. So in chemistry, if something happens kind of by itself, we say, oh, it went downhill in energy. The other thing we need to think about is energy changes that result from interactions between charged particles. There are many charged particles in chemistry because the atom is comprised of positive protons and negative electrons. So let's take a quick look at the energy changes that result from the interactions between charged particles. I'm going to do that with a demonstration, and this is one of my favorite demonstrations. It's a very, very simple demonstration, but it's also a really, really fun one to look at. In this demonstration, we'll be looking at energy changes that result from the interaction between charged particles. Let's look at these interactions between magnets as a model for the interaction between charged particles. First, I'll start with a system where the charges facing each other are the same. They're either both positive or they're both negative. Here you can observe that at large distances there's no visible interaction, and moving one magnet does not appear to affect the other magnet. But as I move the magnets closer together, closing the gap in distance between them, the energy of the interaction goes up. Systems in nature like to minimize energy, so in order to avoid an increase in the energy of the system of both magnets, the increasing force of repulsion causes one of the magnets to spontaneously move away. In a second experiment, instead of having the like poles of the magnets facing each other, what if I turn the blue one around? Now I have the negative pole of the blue magnet facing the positive pole of the gold magnet. Again, at large distances, there's no visible evidence of interaction. They're just too far apart to feel each other's presence. But this time, as the two charges approach each other and get closer and closer, they are attracted to each other because the lowest energy is the case where the opposite charges are close together. They would like to be together, so one of the magnets moves. The Coulombic energy of attraction is transferred to kinetic energy. That causes the magnet to move because the lowest energy state is for the opposite charges to be very close to each other. You might have heard the expression opposites attract, and that is what we are observing here. Let's repeat these experiments from a slightly different angle. First, going back to observe what happens when like charges, again, pretend both charges are negative here, are pushed closer together. But this time, I'll be bringing the magnet in from above. What do you predict is going to happen? Oh, I like that one. You can really see how the same charges prefer to be far apart from each other. If I turn the blue magnet over so that the positive pole of one of the magnets is now facing the negative pole of the approaching magnet, what will happen this time? Here comes the approach of the magnets, this time with opposite charges facing each other. You can see that I can even use the magnet in my hand to control the motion of the one sitting on the table, eventually making it jump. The lowest energy state for the opposite charges is the one that minimizes the